Yes, hi, I'm Helena from the Computer Science Department at TU Dortmund, and I'm working in a collaborative research center called SFB 876, and here everything is about resource-constrained data analysis. So I'm a bit from the other side, like other people were talking about computing stuff in the cloud, but I'm computing stuff on small embedded systems. So we are doing parallel machine learning applications on heterogeneous embedded systems like mobile phones. Some of you might think this is crazy, why should we do this? Normally parallel machine learning runs in the cloud, but there's a movement towards moving some of the machine learning work to the clients. Microsoft also has some work on that. And this is because of privacy concerns, or also because many embedded devices have no stable internet connection. So what our project is about, it's about parallel machine learning applications with the regard of parameter tuning. So we have the goal to find the best configuration of an algorithm. So we do algorithm configuration optimization. And we have many algorithms and many specific parameters. And we use this parameter tuning and we run this in parallel. So parameter tuning can take weeks, but the solution is to use model-based optimization. And this is also visualized in this figure. So the rectangle shows basically the regression model, and the two axes are configurations that are proposed for evaluation in parallel, and then they are evaluated, and the model is updated with the results, and based on the results, new candidates are proposed because we don't want to evaluate every possible parameter configuration, because this would take years. So we use this model-based optimization, and this is our application that we want to run on heterogeneous embedded systems, and there we have to face several problems. So first of all, we have very tight resources like memory and also energy restrictions, and second, if we do not respect the underlying architecture, parallel execution can lead to inefficient resource utilization. So most mobile devices have an heterogeneous architecture to save energy. So they typically consist of different processors with different frequencies and memory sizes, like slow processors that consume less energy for small tasks, as well as fast processors consuming more energy for time-critical tasks. And unfortunately, R has so far no high-level support to schedule parallel tasks on specific processors, and our approach is to enable this. So we want to schedule parallel jobs on specific CPUs, and here we also use a regression model that estimates the execution times, so the workloads of the tasks for each available processor type, and those estimates are then used for the scheduling. So how does such a mobile device, like in the picture, look from the inside? So our experiments were done on the Odroid XU3 board. This architecture is also used in mobile phones, like those from Samsung, and it is based on the big little ARM architecture. It includes 4 big CPUs that are powerful and fast, called Cortex A15, where the CPU frequency can be scaled up to 2 gigahertz, and 4 small, slower CPUs. And it also includes a GPU, and we have 2 gigabytes of RAM. And we configured it with Linux, but it can also be configured with Android. So since we have now different CPUs with different speeds, we also want to allocate parallel jobs depending on the workload to the big and the little cores. So what does R actually offer to do this, and what did we have to change? So the parallel package offers the MC parallel function, and that already supports allocation of jobs to specific CPUs, but here we do not have control over the scheduling of multiple jobs. And also, it's more of a low-level function. That's also why MCLapply function is more frequently found in parallel R programs, but MCLapply has no support for mapping to specific CPUs. So our new modified version, HMCLapply, H for heterogeneous, enables this mapping to specific CPUs and also allows for control scheduling. So now I also have a small benchmark where we evaluate the performance. I also later on have the model-based optimization, but first of all, let's have a look on the small example. So this is R code. This is an exemplary variance filter on a matrix, which sometimes is used in gene expression analysis to pre-filter the number of covariants in the training set, and N is the number of replications of the filter. So only top N covariates are kept for further analysis, and now we want to run this filter with different number of repetition in parallel. And to simulate the different workloads, we use a vector N, so we have 20, 40 different repetitions, and we have the affinity, so we have this C vector with a CPU ID, so 4. So 4 is slow, 5 and 6 is fast. And the idea is to map small workloads to slow CPUs and big workloads to the fast CPUs to balance the parallel execution and reduce the overall runtime. So we evaluated this benchmark and we compared it to MCLapply, and we ran it 10 times and on heterogeneous big little architecture, and compared to MCLapply, the new version needs around 20 seconds less. So if we do not balance the different workloads to the runtime of the different runtime behaviors, that could look like the picture above. So here big workloads are mapped to slow CPUs, causing variance in the completion time, and to optimize the runtime, big jobs should be mapped, like in the lower picture, to the fast CPUs. And this small example, we were already able to reduce the overall runtime, but the question now is how could we know how different workloads scale on different CPUs, because this is not obvious. And therefore we use a regression model. This is only on one processor, so this is a classification task, an SVM classification task. We have on the Y and on the X-axis the two parameters, gamma and cost. And the colors are the heat map of the runtime. So we have the real runtimes and the estimated runtimes, and green configurations with cost and gamma are fast running, and blue configurations are slow running. And as those pictures look very similar, the reals and the estimated ones, we can use these estimations for the scheduling to predict the workloads. And the other thing that we're using for scheduling are the priorities of the jobs. So here we have again the run times. On the right-hand side, we have the prediction performance for those configurations. So here high performance is yellow and low performance is red. And we want to find short-running jobs with a high performance. So, but we don't want to run every possible configuration here for gamma and cost. And to find the best one, that we use a model-based optimization, and this is all integrated in the resource-aware model-based optimization framework called Rambo, which is also on GitHub and based on the MLR MBO package. And here we have 3 steps. We have the MBO methods, the job scheduling, and the job selection and the scheduling. And we have different scheduling methods also for cluster systems, homogeneous stuff. But now I want to show you the benchmark that we ran Rambo on. So for running our parameter tuning on heterogeneous architectures, we use 2 established continuous test functions for model-based optimization from the smooth package. As an objective function, we use the Eckley function. It looks like this funnel, and this blue spike is the optimum, and it also has a lot of spikes in between. And now we want to find the x1 and the x2 that leads to the smallest y. So we want to find the global optimum. And as the Eckley function is an illustrative test function, it has no significant runtime, and that's why we simulate the runtime behavior with the Rosenbrock function. So basically, the parameters of the input space of the Eckley function are mapped to the parameters of the Rosenbrock function. So let's first have a look on how the runtime estimation looks like. So we have here the fast CPU, Cortex A7, and the slow CPU, Cortex A15 I meant, and Cortex A7 is a slow one. And every dot in this picture is an evaluation of an algorithm configuration. So the upper part shows the real runtime, and the lower part is estimated. and the x and the y-axis are the parameters of the ECLA function. And dependent on the parameter configuration, we have different runtimes. So blue are short-running configurations, and red are slow-running configurations. And as we can see, the estimation and the real runtimes are pretty close to each other. We also see that the behavior of the runtime reflects the Rosenbrock function. And in general, there were more evaluations on the fast CPU compared to the slow CPU. So let's have a look on how this looks in the scheduling. So this is an illustration of the scheduling for benchmarks with Rambo on the upper part and the default version without respect to the heterogeneous architecture on the lower part. And we have in blue the slow CPUs and in yellow or orange the fast CPUs. The gray boxes show the mapping of the jobs. So on the x-axis, we have the hours that we needed for the optimization, and on the y-axis, we have the different CPUs. So we have 4 CPUs. And each gray box is a job, or the job runtime, and empty spaces are the idle times, and those vertical lines are the end of this MBO iteration. And our scheduling balances the execution time more evenly, as we can see, and we also managed to evaluate much more jobs. So let's have a look on how the resource-aware scheduling influences the runtime of the best configuration. So this graph shows who find the best configuration first. And on the y-axis, we have the runtime of the optimizations, and on the x-axis, we have the distance to the optimum. So here, 0 would be the target value. So here, lower is better. And as we can see, due to our scheduling, we converge faster to the optimum by respecting the heterogeneous architecture. And after 1 hour, only Rambo managed to get very close to the optimum in all 10 repetitions. Yes, and so it really works good. So let's sum up. So we enabled efficient scheduling for parallel R programs on heterogeneous embedded systems. We extended the MCLApply function with CPU affinity parameter, allowing to allocate tasks to specific CPUs for improved resource utilization. And key to our approach is a regression model that estimates the execution time of a job for each CPU type. And in combination with our scheduling, we were able to optimize the overall execution time of our parallel machine learning benchmark. And we are also on GitHub, so we developed a tracing tool called Tracer, where you can also find the bottlenecks in your parallel R program. This works on every computer, it's not restricted to heterogeneous embedded stuff. And we have different benchmarks, and also our Rambo framework with a different scheduling method is also on GitHub. Thank you.